Good evening, ladies and gents. Wanted to make a video here. I featured this board in a video I did last week, and I kind of wanted to actually dig into this thing and figure out what failed with it. I'm an HVAC technician by trade, so I diagnose failed boards in the field all the time, but I never really have the time to really dig into it and figure out what caused the failure. So I wanted to attempt to do that with this one and kind of show you guys how to approach this sort of thing. The first thing is to, look at what failed on the board, obviously. So this is a board, a control board from a Marvair wall mount HVAC unit, and it was a heat pump, I believe, and its job was to keep an IT room cool. And the specific failure point on this was these two spade terminals right here and here. They were connected to the coil of a contactor, kind of like this. And so there's a coil on the back of this, and when you flow a current through it, it causes the relay to pull in and turns the compressor and the fan on. So the failure point for this was that I had 24 volts to ground on both sides here. So these were even potential. So when you have a coil like this and there's no current being drawn by it, or a resistor for that matter, if there's no current through it, there's not going to be any voltage drop across it, right? So that was why I had 24 volts on this terminal here. And what happens inside of this board, if we were to flip it over and take a look here, this side connects to this part of the relay. And this large plane that you see right here is ground. It taps back to this common terminal right here. So look, that connects there to all of that ground plane, and that connects to this side of the relay. So this is your normally open for the relay. If you were to look up a data sheet for this specific relay, you would find that this is your normally open, this is your normally closed. Now the normally closed is not being used at all. But when this relay closes, what happens is this will sit at 24 volts until the relay closes. And then once it closes, there's a path through the relay into ground for current to flow, which closes that contactor coil. Now that was not happening when it should have. I had a voltage here on Y, which is your control signal, to ground, or to common, I guess, and it still would not pull in. It still wouldn't do what it was supposed to do. So if we were to trace this circuit out, if we look here closely, the coil has two sides to it as well. There's a coil inside of this relay, and that coil is on these two little pins right there. In between, let me find something to point with. In between here and here is your coil, and it follows the same principle, only on a smaller scale. So what happens is this Q3 right here is a transistor, and this transistor is being used as a switch to drive this coil. So you can see what they're doing is they're controlling everything with this microcontroller right here, and they're using these step-ups like this. So this is your lowest voltage, then it goes to your medium voltage here, and then this controls the highest voltage load. So they're using a series of switches to activate that contactor coil. So if we were to look at that coil, we know that it's across from here to here underneath there. And you have this right here. This CR5 is a diode. And I'll explain what a diode does. A diode it's only designed to conduct in one direction. So let me see if I can find one here. I do have one right here that I can show you. It's a little more illustrative than the one that's on that board because it's not labeled or polarized, really. It's not made to look polarized. But this is what a through-hole diode looks like right there. Focus. So you notice how it has a gray band on that side? That's its bias marker. All right, so you have a diode here. It's a semiconductor. And when you flow, like when the voltage on this side is greater than the voltage on this side by around 7 volts, it'll start to flow current. But then it blocks current in the other direction. It doesn't conduct in the other direction. Not only does it block current, but it also blocks voltage as well. So that's the main difference between conduction and resistance. So this only conducts in one way, and it takes a mighty voltage to overcome that and cause it to flow current backwards. There are some diodes that are designed to do that, but we'll not get into that right now. So this diode, the purpose of it is to prevent inductive kickback from this relay coil. So when this relay coil gets turned on by this transistor, what happens is the relay will draw, like the voltage across the relay will be really high at first, and it won't flow very much current the moment that this transistor turns on. And the reason for that is that this is an inductive load, and inductors, the current that flows through an inductor can't change instantaneously. It takes time for it to do so. And the reason why is that when you put a voltage difference across an inductor, the very first moment there's no magnetic field, and an inductor stores energy in a magnetic field. What it does is it converts electrical energy into magnetic energy, and in order for it to do that, it consumes the vast majority of the current at first, and then after some time with DC, with direct current, the current through the inductor will level out, and at that point in time there is no further change in the magnetic field, so it's not going to produce any, it's not going to consume any current to change its size or provide current. We'll get to that. So just think about it like that. The current flowing through an inductor cannot change in an instant. It takes time for it to do so. So let's say this transistor makes, you begin to put a voltage difference across this. It generates a magnetic field, pulls the contact over to the normally open side, and everything's good. The contactor coil should get pulled down, and the contactor coil should make, and the compressor should come on. All right. But the problem arises when it's time to cut it off. So when this transistor moves from being on to off, there's a funny phenomenon that happens here. All right, so you have this magnetic field that is developed on this coil, and when the current falls to zero, when the switch turns off, the transistor turns off, there's no longer any current supplied. And what happens is the magnetic field will begin to evaporate away. It'll begin to dissipate. And as it does so, the energy that it consumed to create itself, it has to go somewhere. Like, it can't just disappear. The energy that moves into the system has to move out of it somehow. And so what happens is it collapses. And as it collapses, it turns back and converts back from magnetic energy into electrical energy. And so it's called inductive kickback, I believe is what it's called. And so it pumps current out the opposite way that it came in, which means that, say that this is your positive side of the inductor. I don't really know for sure whether that's true or not yet, but let's just say that this one's positive. All right. And when it's positive when the switch is on. Well, what happens when the when the transistor shuts off? The current will still remain getting pushed in the same direction, and therefore this voltage on this side will go negative relative to that one. And the current that's produced by this coil, all it cares about in life is getting back to this other side somehow. It wants to complete a circuit and get back to where it came from. And so everything hits an equilibrium point, right? Well, if there's no diode here, what happens? Let's say we just soldered this out. Okay, so this side is now positive, this side is negative. The electrons from this side desperately want to make it to the other side. And what does Ohm's law tell us? Ohm's law tells us that your voltage is equal to I times R. V equals IR, right? And so we know that this magnetic field is inducing a current into the circuit. Now, it's a small current, this magnetic field is not very big, So there's not very much energy there relative to, you know, what we're used to dealing with, you know. But it's still an amount. It's not zero, right? And what's your resistance if this diode isn't here, faced this way? What happens to that? Well, it's just going to the base of this transistor right here. There's no path. So what's the voltage going to do? Z, like, you know, tiny times infinity is still infinity, right? And so theoretically, your voltage will approach infinity in between these two terminals of this coil. And what's going to happen is you get this super huge positive voltage that develops on the base. It's going to break down this transistor, and it's going to find its way into this microcontroller. It's going to find its way to ground. It's going to destroy the transistor. Probably, yeah, definitely the microcontroller too. So what happens is you put this diode here and you reverse bias it, right? So this is your positive normally. If it's faced this way, then when the relay, like during normal operation, this diode's reverse biased and it's not going to conduct this way. But what happens is when the transistor shuts off, the polarity of this coil flips, and now it can conduct that way, and it provides a path, and it allows the current being put out by that magnetic field to dissipate, and the voltage will never rise because you're always giving it that easy path back, All right, so that's why this little diode here is necessary. So getting to the transistor, I'm probably going to start there because it looks like this transistor drives this relay coil right here. So I'll probably start there. Let me zoom in here. And what I'm going to do is, just to make absolute sure, I'm going to start ringing stuff out with my meter here. So I've put my my multimeter in continuity mode, and I'm just going to verify, hey, this is connected to this. All right, so good, we're good there. So I'm going to assume that this is the base because usually the one that's alone is. Let's look at the back here. Oh yeah, so that's the solder pad for that. So we know that this is most likely going to be your emitter because it goes straight to ground. And then this one has got to be, actually, no, this one's your base. I'm sorry. That's going to be your collector. I'm so stupid. But your base is right here. And let's see where it goes. Let's see. So this is your base. And what I'm going to do is I'm just going to drag my probe. Let me get in better. This is really hard to see. I'm sorry. It's hard to film this stuff. All right. So, got here, and then we're going to ohm down these. Nothing. Try again. Try a couple of different things. Really? There it is. Okay, so that's our connection to the base. And what this thing is going to be, this is going to be a base resistor right here. And what this does is it limits the current through the base to the emitter, right? Because if you overload that, it's really hard on the transistor. It pushes it in a hard, what they call saturation. And it's just not good for it. So what I'm going to do now is I know that this one is my resistor, this one right here that I've got my black lead on, and it's going to this pin right here, and we can just make sure that that path is complete as well. I know my camera work is so shoddy, but yeah, so we do have a path. There's no breaks in the trace or anything. So what I want to do now is check the diode across this to make sure it hasn't failed, because if it does fail, like I mentioned before, it's going to burn up everything. We can also check the transistor at the same time. And what I'm going to do is swap these leads out, turn it on, of course, and we'll grab this. This is really good for testing diodes and transistors. I really like using it for that. So I've got this in the diode setting now, and so what I'm going to do is check across this diode. Okay, looks like we have a path there. There's a diode drop there. And so now what I'm going to do is check Q3. So I'm going to put my positive on the base first, what I believe is the base. All right, so we do have a path there. Now let's check from base to emitter. Boom, we got a path there. All right, so we look like that transistor's okay. All right, so now what I want to do, what could I do? I need to check this resistor right here that we looked across. I can do that with these leads. So this resistor right here. And if we look at the value, I'll show you how to read a resistor and figure out what it should be. So that says 4641, right? And what that means is 4.6K. All right. So we need to check our resistance and range. We need to rearrange our LCR meter here to around 20K. And that will allow us to check these. And I'll just go ahead and check them all here. I'm going to get a little bit more light on this board so I can see. So there's our resistor in question. 4.65K. This one, 4.64. And then this one. So those are probably my 3 base resistors for all of the relay transistors. And they all look okay. So I'm not going to pursue that any farther. What could we do now? What could we do? Let's see. So it looks like the diode's okay. Looks like the transistor's okay. Let's check the relay coil for inductance. So remember, it's the small one to the small one here. I can probably check it with this. Let's see. It's not going to read anything on resistance, most likely. This is a 24 volt relay. So I don't really know what to expect looking across it. Looks like it's 1.5K across. Now let's check its inductance. We got 9.2 or 924 millihenries here. So it looks like the coil's good. The coil's not open or anything. Plenty of inductance there, so it doesn't look shorted. So what could we do now? So let's check our positive voltage going to these diodes. So if you notice, these two diodes, this diode has the same job as this one, it's just for a different relay. And so this is going to be your positive side because these two are tapped together. So the transistor kind of works like this works, as I described in the start of the video. So there's always going to be a positive voltage here, and it's going to feed through the coil up to the collector of that transistor. And when the transistor turns on, the collector conducts to the emitter, and it grounds this out, causes current to flow through the coil, just like this one does. It's called low side switching. And so we know that this is going to be our positive side now, so we should see a path somewhere between that. So what I'm going to do is I'm going to use this one again. It's still in the ring mode. And let's check across these, make sure they're connected. Okay, that's good. Now I want to check from this one to the coil. It looks like it goes under there, right? It looks like it goes under that coil into it right there, and then out of that to this. All right, so it's got to go to these other two diodes here. This is going to be your positive side for that one. That one's going to be a positive side for something else. Don't know what. Oh, I'm not sure what that one's for yet. So let's ohm out this coil. Okay, nothing. There's resistance there, so that's okay. 540. Is there a path between here and here? There is. All right. So let's check from there to the coil. That one right there. There's nothing there. All right. So just to verify, this side of the coil touches this. So I should have a path from here to here. I do not have a path there. So I wonder if this trace isn't broken underneath that relay. So I'm gonna get off camera here and desolder this, and I'll be right back. Alright guys, so I've got this board unsoldered here, and look at what I found. Oh no. Oh no. Couldn't see that when it was sitting here, when it was actually soldered in. But once you get it out, there's no path there. That's burnt up pretty good. So it looks like, I don't know. I mean, it's like, this is still gone. I've wiped it off and it looks a little bit better now. But I still don't think that there's a path through there. So let's try this. Oh, I got that on my hand. Alright. So I've got my meter, just knock it over, I guess, and whatever. So let's check from here to here. There is nothing there. There is no path for that. Alright, so our voltage for this positive is coming from this way. This is your power supply right here. This diode is a half-wave rectifier right here. So you can see it's coming off of your 24-volt AC, and it's chopping off the negative portions of the wave. Coming through, goes to this resistor, and gets filtered with these two caps right here. And I'm assuming that it breaks off at some point and gets regulated. This is a Zener diode. I won't get into those right now. There's a lot to them. But that's probably a 24-volt Zener there, or maybe higher, and then goes to all this filtering and then to the coils of these relays. So it looks like we found our problem, dude. You can do a lot just electrically if you follow a process and be disciplined about and rigid about the things you test. You're not retesting and hopping around all the time, you know. It happens to me just like it happens to everybody else. You get overwhelmed with something, a problem you can't figure out. But if you can just stay calm most of the time, it's really something simple like this. I love you guys. Take care.